to in-class exercise 3 or 3B, position vector and calculating force vectors using position vector. For this problem, by the way, this problem is on page number 19 of your master handout, in-class exercise 3. So we are working on this problem, and once we solve this problem, you will be able to solve the remaining problem on page number 18 and 17 on your own, because those problems are very similar except that they have different values of dimensions and magnitudes of forces, but the procedure is the same. So let's work on this problem. Determine the magnitude and coordinate direction angles of the resultant force acting at A. So this is the light pole, and we have two forces, and the light pole is attached to the ground using two cables, AC and AB. And each cable has the magnitude of the force as given here, which is 900 and 600 newtons respectively. The locations of these connections with the ground are defined in terms of the dimensions relative to the origin, which is at the bottom center of the pole. So this point is 0, 0, 0, x0, y0, z0. Positive x is in this direction, positive y is towards right, and positive z is going up. And what we need to do is we need to find out that what is the total force that acts at A, which is combination of FB and FC. Now we cannot simply add this together like 900 plus 600 equal to 1500, because that would be wrong, because these are just the magnitudes and force is a vector. We cannot add only magnitudes of vector to find the resultant magnitude. We need to write each force as a Cartesian vector of I, j, k coordinates, and then do vector addition, find out the resultant force, and then calculate the magnitude and coordinate direction angles of the resultant force. Okay, so our procedure is step number, we will define the coordinate system, so that we already have defined here in the problem. Second step is we have defined the direction for the coordinate system for x, y, and z. So this is positive y, and this is negative y. This is positive x, this is negative x, and that's positive z. Third step is we will calculate the coordinates of the points of interest. So these points are A, B, and C. We will write down coordinates of each point. So point A is straight along z-axis, so it has 0 value of x, 0 value of y, and positive 6 value of z. So A has 0, 0, 6. That's the coordinate system. Point B is in xy plane. Its distance from origin is 4.5 meters at 45-degree angle. So we need to find out the projection of this line on the x-axis. So it's 4.5 cosine 45. That will give us the x coordinate, because this is 45 degrees, so this angle is also 45 degree. So 4.5 cosine 45 is the x coordinate, and that's along the positive direction. Y coordinate is along this direction. It's here, this distance measured from origin, and that distance is also 4.5 sine 45, but it's negative because it's going in negative direction. So it's minus 4.5 sine 45. Now since it is in xy plane, it does not have any z coordinate, so z coordinate is 0. Point number C, which is here, sorry, point C, which is here, it's 3 units along negative x, so it's minus 3. It's 6 units along negative y going this way, and it's given here 6 units, 6 meters, so it's minus 6, and it's 0 along z. So step number 1, we write down the coordinates of these points, both AB, all A, B, and C. Now the next step is we calculate the position vectors going from A to B. So RAB, vector which goes from A to B, and we write this depending on the direction of the arrow. So see, the arrow is going from A to B, so we will write that as RAB, which is equal to coordinates of point B minus coordinates of point A. Now 4.5 cosine 45 is 3.18. So this is 3.18. Let me write this here. So B is now 3.18 minus 3.18 and 0. This is 4.55 cosine 45 is 3.18. So we can subtract the coordinates of A from coordinates of B, and so it's 3.18 along X. So that's coordinate of X. A has 0x, so it's minus 0, and the unit vector in that direction is positive I. For Y, B has value minus 3.18. Minus this negative sign is because of the equation here, 0 and J. For Z, B coordinates of point B are 0, minus A has 6, and unit vector in that direction is K. So this is 3.18 I minus 3.18 J minus 6K. That's the position vector going from A to B, and it has the unit meters. Now we need to calculate the magnitude of this vector as well. So magnitude of vector AB, which is square root of this 3 component square, and that is 7.49 meters. So how do we get 7.49? Is square root of 3.18 square plus 3.18 square plus 6 square, and that is 7.49. We do the same thing for vector going from A to C as well. So this vector along this cable going from A to C. So RAC equals coordinates of C minus coordinates of A. Now coordinates of point C are minus 6 minus 3 minus 6 and 0, and A are 0 0 6 along X, Y and Z respectively. So C minus A means minus 3 minus 0, minus 6 minus 0, and 0 minus 6. So all three numbers will be negative. So it's minus 3 minus 0 plus minus 6 minus 0 along Y, and 0 minus 6 along Z. So these coordinates are minus 3I minus 6J minus 6K. And again, this is unit is meters. We calculate the magnitude of vector AC, which is square root of minus 3 square plus minus 6 square plus minus 6 square, and that is 9 meters. Okay, so for both position vectors, we have calculated the magnitudes as well as Cartesian representation of the vectors. Now it's time to write down the force acting along cable AB. So FAB is equal to magnitude of that force multiplied by direction. And direction we will write in terms of position vector divided by its magnitude. So it's RAB divided by RAB. So magnitude of force acting along AB, which is this cable, is given as 900 newtons FB. So it's 900 multiplied by 3.18 I minus 3.18 J minus 6K divided by its magnitude, which is 7.49 that we have calculated in the previous step. Now remember that there is no unit of this bracket because this is meters divided by meter, so it's dimensionless, multiplied by Newton. So at the end we get the unit, which is Newton. So when you do this math, you need to divide 900 by 7.49 and multiply that number with each one of this component here. 3.18 minus 3.18 and 6. So it's 382.10 I minus 382.10 J minus 720.96 K. And this is now newtons because that's the force. So we have calculated force AB as a Cartesian vector. Now we need to do the same thing for vector AC as well. So let's do that on the side here. So FAC is equal to FAC magnitude multiplied by direction. And direction we derived from position vector, so it's RAC divided by RAC, where RAC in the numerator is vector and in the denominator it's the magnitude of the vector. Now magnitude of force AC is given here, that is 600 newtons. So go back and substitute that here. So it's 600 newtons multiplied by RAC divided by RAC, which is minus 3I minus 6J minus 6K, divide by its magnitude, which is 9. After multiplying this components, we get the vector for AC as minus 200I minus 400J minus 400K. And this is also force, so it has the unit of newtons. So we have both force AB and force AC as 3D Cartesian vector that we can see here. And then last and final step is to add those two vectors. So we can say FAB plus FAC, which is minus 200I minus 400J minus 400K. And then addition of these two is our resultant force FR. So we just combine I components with I components. So it's minus 300 multiplied by, minus 382 minus 200. So that is positive 182.1I. Then it's minus 382 minus 400. So that's minus 782.1 J, and it's minus 700 minus 400, which is minus 1120 K. And that is the resultant force acting at point A, which is combination of both AB and AC. Now we need to calculate the magnitude and direction coordinate angles for resultant force. So magnitude of resultant force is square root of this 3 component square, which is 182.1 square plus minus 782.1 square plus minus 1120 square, and square root of that, and that is 1378.12 newtons. We can also write this as 1.38 kilonewton using our units rules defined in chapter 1. Okay, so I have used kilo because I have replaced 1300 by 1.38. So this kilo is 10 to the power 3 multiplier. And the direction angles can be calculated using equation alpha is equal to cosine inverse x component, which is 182.1, divided by the magnitude, which is 1378.12, this number here, and that angle is 82.4 degrees. Beta, which this force makes with y-axis, the angle is cosine inverse of y component, which is minus 702.1 divided by 1382.12, and that's 124.57 degrees. We can write this as 125 degrees as well. And gamma is cosine inverse of third component, which is this minus 1120 divided by 1378.12. Sorry, there is typo here. It should be 1378.12. And then this angle is 144.36 degrees. So we can round all of them to like 3 significant figures. So it's 82.4 degrees. This is 125 degrees. And this is 144 degrees. So these are our final answers. So let's go back to the question. Determine the magnitude and coordinate direction angles of the resultant force. And so this is the magnitude of the resultant force. and these are the coordinate direction angles of the resultant force. So these are our final answers. Thank you.